So for the last little bit of electrochem, we're going to talk about something called electrolysis. So when we did voltaic cells, we used spontaneous reactions, reactions that would just happen that we could harness the electron movement and create electricity. Electrolysis, we are going to focus on thermodynamically unfavorable reactions and how to get those to happen. So voltaic or galvanic, which are the same thing, are based on thermodynamically favorable redox reactions. E naught value is positive. However, electricity can be used to force a non-spontaneous thermodynamically unfavorable reaction to run. So in that case, E naught is negative. When we make those happen, we call it electrolysis, and we say the reaction happens in an electrolytic cell. So it's important that you know the difference here. Voltaic and galvanic cells are spontaneous reactions. Electrolytic are not spontaneous. So let's take a look at one of these. So if we melt NaCl, so not dissolving it, take solid NaCl and make it molten NaCl, we can push some electricity through the melted NaCl. We will force the non-spontaneous reaction to occur. Okay? So what you can do is write out the possible half reactions that could occur at the anode and the possible reactions that could occur at the cathode, and then decide which ones are happening. So in order to do this, something you're going to hear me say a lot in this topic is think about what's actually in the container. So the half reactions that will occur here is we have Na plus and Cl minus in our container. So the only options we have for reactants are Na plus and Cl minus. So this cannot occur because we do not have solid NaCl. Or excuse me, we do have solid NaCl. We do not have solid Na, solid sodium. We also don't have Cl2 gas. We have NaCl together, and we have Na plus and Cl minus. Okay, so our only two options are here. So this question is asking you what happens at the anode. You know anode is oxidation. That was in a prior video, anode oxidation. So you're going to pick, you have two options. You have this one and this one. You pick the one that has oxidation happening. Here you can see we have reduction. Na plus is becoming Na. Here Cl minus is becoming Cl with no oxidation, with 0. So that's your oxidation reaction. So your answer here is going to be this one. Another way to think about this, and that might come in handy later, is that an oxidation reaction is always going to have electrons as its product. Okay, oxidation half reaction. So sometimes it is easier just to look at that if you're given half reactions rather than trying to figure out oxidation numbers for some of them. For these two, it's pretty easy to do either one. So here are what we decided. This is going to be the anode, and this is the cathode. Now, neither one of those things is going to be spontaneous, going from Cl minus to Cl2 or Na plus to Na, but we can force them to happen by adding electricity. So we use a voltage source to provide the energy to make this happen. So here you can say we have this voltage source and we're forcing those non-spontaneous reactions to happen. Write out all the possible half reactions that might occur at the anode and the cathode. So in this case, we have a split cell. We have KBr NaCl, cathode here, anode here. So the possible half reactions would be 2Cl minus, just like that. And then our other oxidation reaction would be Br minus, because in this case we have Cl, NaCl and KBr. So those are our possible oxidation reactions. Our possible reduction reactions are this. So this isn't like the last one that we looked at, because in the last one we looked at, we said, oh, okay, these two we can cross out automatically because we don't have Na or Cl2 in our container to start. But here we do. When we force molten KBr and NaCl, we can get these ions. We can get Cl minus, Br minus, Na plus, K plus. So now, how do we figure out which one is happening? So these are both oxidation. And the way to figure out which one actually occurs is which one is quote unquote the cheapest. So if you look up the E naught values on your standard reduction potential table, you would see that E naught for this one is negative 1.36 and E naught for this one is negative 1.07. Now we know we would flip those because they're oxidation, whatever, it doesn't matter. What you then look at is which one of these has a smaller magnitude. So the plus and minus doesn't matter, you're looking at the absolute value. That's when we say it is the cheapest, it costs the least. So here, obviously 107 is smaller than 1.36, and we're not talking about the negative sign, so just look for the smaller magnitude. So you pick the one that is the cheapest. So this is the reaction that will occur at the anode. Now we do the same thing for our reductions. So Na plus to Na has this E naught value. And the K1 has this E naught value. So looking at the absolute values of our two E naught values, we can see that we're going to pick the cheapest, which is the Na one. So this is going to be our cathode. And it doesn't even matter that they're not the same. Okay, it doesn't even matter that they don't come from the same compound, that it's not like Br and K or Na and Cl, it doesn't matter. Now, just a side note, E naught doesn't technically apply to liquids, only aqueous solutions, but we can use them to see the relative ease of these and figure out which one is quote unquote the cheapest. So these numbers don't matter as much as we can use them to compare each other. So here we have decomposition of water into its elements, the two half reactions that contribute to this decomposition, and calculate the voltage of the reaction. The best way to do this is to look at your standard reduction potential table and write out the two reactions that involve water. The two reactions that involve water are this one and this one. But in our equation, We can't add these two together to get this because water is not a product anywhere. Okay, so what we'll do instead is flip this reaction and then change the sign of our E naught. So if we do that, and I'll just write the E naught values over here. We'll get negative 1.23. And then for our second one, we keep that sign the same because we didn't change anything. So now let's make sure the reactions add up to get our overall reaction that we wanted. Okay, first thing we need to do is make sure the electrons cancel. So that means in order to get these 4 electrons and 2 electrons to cancel, we're going to have to multiply this reaction by 2. Okay, now remember that doesn't change the E naught. We said the stoichiometry of that doesn't change E naught. So I am going to change this to a 4, this to a 4, this to a 4, and then also a 2. Oops. So now my electrons will cancel, and I'll end up with 6H2O gives me O2 plus 2H2 plus 4H plus 4OH minus, which is still not what I wanted. But look, this right here, H plus 4OH minus can become 4H2O. Those will combine. Okay, then this 4H2O will cancel with 4 of those, and we will end up with the reaction that we actually wanted. And that's something you're probably going to have to do a lot. Combine H plus and OH minus to get H2O in this type of reaction. So now that we know we do have the correct thing, you can just add these together. And your answer is this one right here. All right, so let's move on to another cell, potassium iodide. Think about what is actually in the beaker. If we have a potassium iodide solution, that means we have K plus, I minus, and H2O, because solution means it's in solution with water. So it dissociates into K plus and I minus. So we have 4 potential half reactions if we look at our standard reduction potential table. We have the 2 for water, and then we have the K one, and the I minus one. And this is what I was saying before, to figure out which ones are oxidation and reduction. It's really helpful for the water ones. If you just look, oh, this is giving off electrons, so it must be oxidation. And this one is taking them in, so it must be reduction. So let's take a look at what reactions would we have an option at the anode, okay? So at the anode, we know it's oxidation. So go back up to our 4 and pick the 2 oxidation ones. The 2 oxidation ones, we just said this one is oxidation. And we said this one, you can see that one's nice and easy to see, is oxidation. So now look up the E naught values. And pick the cheapest. So look at the absolute value and pick the smallest absolute value. So this is going to be our reaction at the anode. So now we're going to do the same thing for the cathode. Our 2 potential reduction reactions are the water one and the K plus. So the cheapest one is going to be this one right here. So that's going to be our cathode reaction. Okay, so that's what it is. Basically just picking what reaction is going to happen. First thing you do, think about what's actually in the container. Next thing you do, figure out which one is cheaper out of your options for cathode and anode. So now we're going to talk about quantifying electrolysis. And quantifying electrolysis is a lot like stoichiometry, okay? There are other ways to do it. So in some of the answer keys, you'll see kind of other things, but I really think the easiest way to do it here is using stoichiometry. So what you do need to know for your stoichiometry is really this number right here, okay? So we have the charge on 1 electron is right here, and that is a number that I know and I used at some point, but you don't really need it. What you do need here is the charge on 1 mole of electrons, okay? And you'll find that on your formula sheet. We're also going to be using this a lot, and you'll see that. Coulomb is a measure of charge if you haven't heard that word before. So you're going to see that, like, it's going to be just a kind of conversion factor that we use, okay? 1 amp is 1 coulomb per second. So that, I think you see this or this on your formula sheet. And we will use that quite a bit, okay? And then if you want to see the derivation, we know that the charge on 1 electron's up here. That's the one we don't really use that much. Times 1 mole of electrons gives us the amount of coulombs that are in 1 mole. Pretty straightforward. So these are the types of questions that are going to be asked. And for this video, we're going to kind of build on the same reaction or the same cell for a little while and then switch to another one. So here, if you ran the system for 2 minutes at 0.5 amps, the amount of electrical charge in coulombs that is passed is, and let's find that out. So we know from up here that current is equal to charge over time. So our current is here, and charge is what we're looking for, and we have time, okay? Amps is going to be equal to coulomb over seconds. So instead of 2 minutes, we'll use 120 seconds. So if we're looking for coulomb, so that's charge, we just do amps times seconds. So coulomb equals amps times seconds. So we get a total of 60 coulombs in those 2 minutes. Okay, you'll notice that the reactions don't even really matter here. I didn't use anything in there. It will sometimes, we'll talk about that in just a minute, but right here I didn't even need that reaction. So now we're going to talk about this system for a little bit. If you ran the same system for 2 minutes at 0.5 amps, the moles of electrons transferred is blank. Okay, now we know the charge. So we can just use that charge to solve for the moles. You can also start at the beginning and go all the way from amps times to get amps times seconds is coulombs and then do that, but we already have that number, so why bother? So if you look up here, we are going to use this number, coulombs per mole. Okay? So we have 96,485 coulombs per 1 mole of electrons. We are looking for moles, and we know that our coulombs, that's total transferred, is 60. So this is where you can start that stoichiometry. So if you start with your given of 60 coulombs, and you multiply that by this factor, except obviously we're going to flip that over so that coulombs will cancel. Then your coulombs will cancel, and you'll end up with just moles, which is what you wanted. So when you do that out, which is this right here. And we're just going to keep building on that. So if you have a grasp on stoichiometry, this is very similar. Like I said, there are other ways to do it, but I really think the stoichiometry is the easiest way because you're pretty familiar with that. So if we did the same system, same conditions, how many moles of iodine would we form? And that's where the reaction starts to come into play, okay? So here's our reaction. And if we're talking about iodine, we can split it up into the iodine half reaction. 2I minus gives us I2. And then obviously we need to add 2 electrons to that. So we are looking for moles of iodine. We have moles of electrons from our last problem. So we can take that number and use the mole ratio of our half reaction. And if you're wondering how I know it's I2 and not I minus, it's because I minus is the iodide ion and I2 is iodine. It asks us for iodine, also formed, meaning a product. So now we just need the mole ratio. So we can use our half reaction. There's no number in front of I2, so that's going to be a 1. There's 2 in front of electrons, so that's going to be a 2. And when you do that out, you get that you form this many moles of iodine. So again, just basic stoichiometry stuff. So let's take that one step further and figure out mass, okay? For this one, I obviously know I know you know how to go from moles of iodine to mass of iodine. So what I'm going to do is start at the very beginning here. Okay? I'm going to show you if you just were asked this question, not all the ones leading up to this, how would you get to the answer? And you would just do basic stoichiometry, okay? So we're doing 0.5 amps. 0.5 amps is the same as 0.5 coulombs per second. We are going to run it for 2 minutes, so we can do that's 120 seconds. We want to get to mass of iodine. Okay, so to me that says I want to change coulombs to mass of iodine, grams of iodine. So I already did seconds. I got rid of seconds, right? Seconds will cancel. So that's great. I don't have to worry about seconds anymore. Super, because I don't want it in my final answer. So now I can just worry about changing coulombs into iodine. And you have to think, what's the link there? Moles. Moles of electrons, moles of iodine. Moles is always the link to everything. So we'll take the coulombs to moles of electrons. Then we can use our mole ratio to get moles of iodine. And then the molar mass of iodine. And so that when you do that all, you'll see that everything will cancel. So coulombs cancels, moles of electrons cancels, moles of I2 cancels, and we end up with just grams of I2, which is what we wanted. Great. So grams of I2 Okay, so this is new because we're throwing in this coulomb bit and you have to get rid of seconds and you have to really think about what am I looking for at the end here? What do I need to cancel? How do I make that happen? But you already know this process of dimensional analysis. You're very familiar with it. So I think this isn't really that bad. You just need some practice with it. Okay. This is the same system, okay? So now we're changing it. Instead of mass of iodine, we're changing to volume of hydrogen gas. Okay? So we know that 2 moles of electrons are transferred in this reaction. And if you want to write out the half reaction for just the hydrogen gas, so the H2O gives hydrogen gas and 2OH minus, and you'll see that it's 2 moles of electrons, that's true. But I'm just going to write myself a note here that it's 2 moles of electrons that are transferred in this reaction. So what you will do, and I'm going to do this from the beginning, pretending I don't have any other information like moles of I2. Obviously, I have that. It would be very easy to get to moles of H2. Okay. I'm going to pretend I don't have that and start at the beginning, just like I did with the last one. So we're going to start with coulombs per second. And you want to think, okay, what am I trying to get to here? This says volume of hydrogen gas. So there's 2 ways to get there. It's at standard conditions. So my guess is you could probably use 22.4 and just do regular stoichiometry that way. Maybe someone should do that and test it out. I'm going to use the ideal gas law. So I'm going to try to get to moles of H2 to plug into that ideal gas law. So for every 2 moles of electrons, how many moles of H2 do I form? Just 1. Then I can find volume by just plugging everything in here. So this should be your answer. And you should get just around that if you just did the same thing, except kept going on your stoichiometry to 22.4, because these are at 25 degrees Celsius and 1 atm. The reason I wanted to do it this way is just in case AP throws something at you that's not at standard conditions, meaning you couldn't use 22.4, this is how you would do it. Okay, you can use the gas law this way. Okay, so now we're going to take a look at, kind of abandon that cell and move on to this zinc cell, okay? And this is nice because we don't have the ones leading up to it, so we do have to just do our long stoichiometry problems. If an electrolytic cell was allowed to run at 1.5 amps for 2 hours, what mass of zinc could be deposited into an electrode from a zinc nitrate solution? Let's do this, okay? First thing I would do, so that I have all the information I need, is figure out how many moles of electrons would be transferred here, okay? You can do out the reaction, or you can also think zinc. Zinc's charge, always, even though it's a transition metal, is 2+. So that means we're going to have 2 moles of electrons for every 1 mole of zinc. I'm probably going to need that. So I would just put that right up there. So once I get into my stoich, I don't have to worry about it. So then we can do our 1.5 amps, which is just going to be coulombs per second. And then we have 2 hours. And we know that for every 1 hour, there are 3,600 seconds. So that will take care of getting rid of our time. Right? Because seconds cancel and hours cancel. So now we just have to focus about turning coulombs into mass of zinc. So we'll convert coulombs to moles of electrons. And then we know, because we did that at the beginning, every 2 moles of electrons gives us 1 mole of zinc. And then we can just multiply by the molar mass of zinc to figure out how many we have. All right, now we get into a little more tricky ones. Not something you can't do though. Calculate the molar mass of a metal which was deposited from a 3+ ion. So this tells you right here that we need 3 moles of electrons for every 1 mole of the metal. And I'm just going to put capital M for metal. And then it gives us 4.5 amps, 3 hours, 11.7 grams of metal. So the reason this is a little tricky is because you have to stop and think, what am I looking for here? What units? Because it's asking for the molar mass. So you want grams of M over moles of M, or 1 mole, but we can just divide to get that at the end if we don't have it. So this is what our end goal is. So when you're doing your stoichiometry or your dimensional analysis, you want to be able to cancel everything else out. So you can start with your amps, you can start with your whatever you really want to start with here. It doesn't really matter, you just follow the process. I'm going to start with 11.7 grams of capital M metal. And that came over 3 hours. So then I know for every 1 hour, there are 3,600 seconds. And then based on my amps, I know I have 1 second for 4.5 coulombs. And then we have 96,485 coulombs for 1 mole of electrons. And then we know we have 3 moles of electrons for every 1 mole of the metal. Before I do all this math out, I'm going to check and make sure I end up with grams of M over moles of M. So hours will cancel, seconds, coulombs, and moles of electrons. So what do I end up with? Grams of M over moles of M. So now all I have to do is do out that math. 69.7 grams per mole. That is the molar mass of my metal here. I think it's closest to like gallium or something. Gallium. Okay, so again, just thinking through the process of stoichiometry here. .937 grams of chromium was deposited in an electrolytic cell after it was run for 1.55 hours at 1.87 amps. What was the charge of chromium in the solution? All right, stoichiometry problem, but we need to figure out what the charge of chromium is. So what we are looking for is kind of a little weird, okay? So what you're looking for here is moles of electrons over moles of chromium. Okay, and that's because if you look at some of these other ones that we did here, 3 plus charge, we knew 1 mole of electrons for every 1 mole of M. Zinc, 2 plus charge, 2 moles of electrons for every 1 mole of zinc. Okay, so to find the charge, we're kind of working backwards here. We're saying, how many moles of electrons do you need for 1 mole? To figure that out, we put moles of electrons and divide it by moles of chromium just so we get that 1 on the bottom. All right, so I'm going to do this in 2 steps. The first thing I'm going to do is find the moles of electrons. We have 1.87 amps, so coulombs per second. We know that we have 1.55 hours, which 1 hour has 3,600 seconds. And then that will cancel out our times. Seconds, seconds, hours, hours. So now we just need to turn coulombs into moles of electrons. That's pretty easy. We're very familiar with how to do that at this point. So there we go. That's our moles of electrons. Now I'm going to find the moles of chromium. Very basic, easy situation that you would have done in first year chem, taking grams of chromium, dividing by the molar mass of chromium. So now we divide them just so that we can get it to 1 mole of chromium. And we get 6. You have to round to the nearest whole number because you know charge is going to be a whole number. So if you didn't get that perfect because we rounded things or whatever, round to the nearest whole number. Chromium has several oxidation states, which are possible charges, and 6 is one of them, so it works. Okay, now we're looking for amps. So what is amps? Amps is coulombs per second. Okay, so this is what we're looking for. We're going to end up with that at the end of our stoichiometry. So I'm going to start with grams of aluminum. To go to moles of aluminum, we know that aluminum always gets a 3 plus charge. So that's going to be 3 electrons for every 1 aluminum. And then we can use that to convert to coulombs. Of course, that's not what we want. We want coulombs per second. So we can keep going with this, or we can do seconds separately. It really doesn't matter. You're going to get the same answer. So if we looked for seconds, you do 3.5 hours. And then divide. And when I'm doing these stoichiometry problems, you know that there are multiple ways that you could do the math. If you're not doing it in the same order I'm doing it, it doesn't matter. But our answer is going to be 0.85 no matter how you do it. And then our last one is asking for time. So same process, just a little bit different. Okay, we're looking for minutes. So this is what we should have at the end. So I'm going to start with my 3 grams. Ag only has a +1 charge, so it's going to be 1 mole of Ag for every mole of electrons, 1-to-1 ratio. And then our amps here are 1.5 coulombs per second. And then, we do 60 seconds in 1 minute because our answer, they asked us for minutes, so that gives you 32 minutes. I know that was a lot of math, but it was all basically the same thing over and over again, so I don't think that will be hard for you folks to master.